Okay, hi everyone. So last time we saw a little bit of we saw the difference between homology and cohomology of the moduli space of curves, of stable curves. We saw that we do have Poincare duality, even if we have some complex orbifold or the Riemann for the compactification. And also we introduced some of our protagonists. So if you remember, let me recall a little bit what these guys are. So these are the protagonists of the cohomology of MGM bar. Okay. And what do I mean by that? I mean that they are somehow the usual suspects, the classes that you would see the most often and that you can use to build more complicated classes in the tautological ring. So we also mentioned the fact that the cohomology of MGM bar in general can be wild. It can be very, very large and also ill-behaved, has several problems. So what people usually do is to study this tautological ring, which is a much smaller ring, but also we know much more about it. And I was making the analogy, if you remember, that the tautological ring to the whole cohomology ring is a little bit like the matter that we can explain and we're familiar with respect to all the matter, including the dark matter. So we know that we only know very few, very little, but we know so little about what we don't know. So there is much more out there that we cannot explain, but we also don't have so far the tools to describe it very well. So we should be content for now to describe a very small part of the cohomology, but it's also the part that we know the most about it. And we also have a lot of structure and a lot of results. And it's very, very useful also for physics. So I would say that just studying the tautological ring, it can be per se extremely useful. And also most of the Gromov-Witten theory that we can explain so far like that is done in what I'm trying to say is that most of the nice results that we have it inside the tautological ring. And it's very rich of structure and mathematics and physics already. And then, of course, whenever we find something that is not in the tautological ring, we are also very happy and we write a paper about it, just to clarify the fact that we have so few instances in which we can describe something well that is outside of the tautological ring that is exciting enough to make a paper just for that. But we also have very few examples of them. We have like just a bunch of examples of classes that are not in the tautological ring and have some geometric meaning. So if you find one, please let us know and maybe write a paper about it. But you can also write papers on the tautological ring. There is still a lot to explore and to explain. For example, there is this conjecture of Pixton that was somehow, like, I would say, a big deal. And well, this tautological ring has a lot of relations that are very difficult to describe completely, or were very difficult to describe completely initially. And then people started using, like mathematicians like Karl Faber initiated this sort of school of approaching this problem with the computer. So started coding these rings and these relations, started exploring. And then we had this Faber-Zagier tautological relations. And then Pixton conjectured the list of tautological relations and stated that this tautological relations list is complete. So somehow he has a list, believing his PhD thesis, that is meant to be complete. So these are all and only relations in the tautological ring. And I would say in the community, almost everyone believes it. And also people could verify each and every relation. So we know by now, we proved that all of these relations are true. They do hold. Actually, I think the first paper that proved that was by Pixon, Pandaripanda, and Zvonkin. Yes, 3-spin tautological relations. So they proved that all of the tautological relations in this list, they do hold. But somehow the difficult part is now to prove that there is no other relation outside of this list. This is a very difficult thing to prove. But over the years, people came up with different ways of producing a list of tautological relations. And somehow what they have realized is that every time they were producing a list of tautological relations, it was either a sub-list of Pixton's list, or it was exactly Pixton's list. So that somehow reinforced the idea that Pixton's list is correct, or that the methods that we use to produce this list of tautological relations, they always produce Pixton's list. And if we want a chance to find a new tautological relation that is not in Pixton's list, then we have to use a completely different method. So this is the state of the art as of today. But I would say that, yeah, almost everyone I had a chance to discuss this believes the list, that this list is complete, I would say. Anyways, my point is that this ring is already very, very intricate in itself. And it's also very, very interesting and rich of structure and rich of results. And the protagonists are the classes that I wrote here. So if you remember, when you consider MGN bar, so moduli space of stable curves or Riemann surfaces with n marked points, these points are distinct and they're labeled. And the genus is G, and you have this Riemann for compactification in which you added the nodal curves. And they should be stable in the sense that every connected component of every curve needs to have finitely many automorphisms. How do you ensure that a component has finitely many automorphisms? Then you have to ensure that the Euler characteristic of that component is negative. And when does this happen? Well, basically every time except 4 dangerous cases. Let me remind you which cases are they. The 4 dangerous cases, meaning the 4 type of connected components that do not have finitely many automorphisms. So 3 of them, 3 out of 4 are in genus 0. So you just take the Riemann sphere with 0 mark points or 1 marked point or 2 mark points. Those are unstable. And the torus without any mark point, that is also unstable. But as soon as you then have a rational component with 3 mark points or a torus with 1 mark point, that becomes stable. And from that point on, if you keep adding mark points, it's more and more stable. And let me remind you also that when you check stability for a connected component, you have to check stability using all special points. And special points are subdivided into actual mark points, this Pi, starting from P1 and reaching up to Pn. But also, as special points, you count the nodes. So if you have a connected component that is connected by 1 node and has 2 mark points, that would have 3 special points in total. And so you would need to account for all 3 when you compute the stability. Also, let me remind you that for each of these mark points, so P1, Pn, you can consider the cotangent bundle on Pi. So as you move around the moduli space of curves, you keep track of where Pi is in your curves. And you keep track of the cotangent bundle of the curve at Pi. As you move around the moduli space of curves, that gives you a line bundle over the moduli space. And when you have a line bundle, you can take its Chern classes, but because it's a line bundle, you can only take the 0th Chern class and the 1st Chern class, but the 0th Chern class is not very interesting. So you just take the 1st Chern class. The 1st Chern class, we saw that you can compute it explicitly just by taking a meromorphic section of the bundle and then you just take the locus of zeros minus poles, accounting for multiplicity. And then there's a theorem that states that it doesn't really matter which meromorphic section you take, you just take one, the one that you like the most, because it's a topological invariant, so it doesn't matter. And so now when you take this first Chern class of these cotangent bundles, then you find these psi classes. Psi1 is the first Chern class of the cotangent bundle on the first mark point, whereas psi-n would be the first Chern class of the cotangent bundle on the nth mark point. And then what you can do is to take the last psi class, let's say that is, you consider moduli space with n plus 1 mark points, but you're going to forget about the last mark point. So this n plus first mark point, we are about to forget it, okay? We forget it how? Let's remind ourselves that we forget mark points with this map pi. This map pi is the forgetful morphism, and it forgets one mark point, usually the last one, because they're labeled, there is no ambiguity. And also when you forget the last mark points, remember that sometimes the curve can be unstable. So it was stable before with a point n plus 1, but as you forget about it, it may become unstable. And you have two possible instances of this phenomenon, but for each of the two, we resolve the instability, if you remember, because we defined what is the stabilization of those two problematic cases. So we know exactly how to cure this instability as it occurs. But before forgetting the n plus first mark point, what you can do is to consider the psi classes on it, and you can take powers of this psi class. We saw the Witten-Kontsevich potential, and we spoke about Witten's conjecture in 1991, and Kontsevich solution in 91, 92. Well, depending if you count the year of publication or the year of whatever. We know there's a little bit of delay when you write papers and you will publish them. But the point is that this was a very big result. It was a very big conjecture and a very big result in the field, because there were two approaches to two-dimensional quantum gravity, and there was some ambiguity, but Witten conjectured that actually they were the same. They were the same, not the same approach, but the theories were giving the same correlators. So just a second. Yeah, giving a talk. And so the main point is that as you prove that the correlators are the same, you have a complete equivalence between these two approaches. And the way this was done was to prove that the Witten-Kontsevich, what we now call Witten-Kontsevich potential, that is just the generating series of integrals of powers of psi classes over the moduli space of curves, that satisfies the KdV equation, this Korteweg-de Vries equation, if you remember, and that's the equation that describes these soliton waves on canals and all its symmetries. So you don't just satisfy the first equation, but an infinite list of PDEs in infinitely many variables that is called an integrable hierarchy. And of course, because the first equation is the KdV equation, the whole hierarchy is called KdV integrable hierarchy. So in that Witten-Kontsevich potential, if you remember, you saw a lot of powers of psi classes, and this is what we're doing now. Here we're taking the last mark point, psi classes on the last mark point, and we're taking powers of that psi class. Let's take m plus 1 powers, and let's forget about the last mark point. But because now this is a cohomology class, we don't have to take pi of that, but we have to take the push forward with respect to pi of that. And that is a cohomology class that lands in the moduli space, in the cohomology of the moduli space MGN bar. Okay, and of course, you can compute, if you remember, because this is the first Chern class of a line bundle, then it would live in the second cohomology group. So one complex dimension, two real dimensions, okay? So it has degree 1 in the complex sense and degree 2 in the real sense. But now this will be in degree m plus 1 complex. But as you push it forward down to MGN bar, because the dimension of the moduli space MGN or MGN bar, its dimension is 3G minus 3 plus N. When you are in the moduli space with one more mark point, also the dimension is augmented by 1. And therefore, as you push it forward, you are forgetting one mark point, but also you're forgetting one dimension of the space. And so therefore, the result lives in the mth cohomology group in the complex sense, just to clarify. And that's why here you see m+1 that may seem unnatural, but after the push forward, you call this kappa m. And these are called the kappa classes. These are called psi classes. Sometimes the kappa classes are also called Morita-Miller-Mumford classes. And you have these kappa classes for all m greater or equal than 0. Of course, if you're on MGM bar, if you consider m greater than 3g minus 3 plus n, of course, it will vanish. So it's not very interesting. But in principle, you have kappa m for every m if you don't fix g and n. Yes? I'm giving a talk. Sorry. Posso passare dopo da te? Ok, grazie. Yeah, so the first kappa class that you have is kappa 0. And kappa 0, in fact, is just a number. So you may ask yourself which kind of number this is. And this number is 2g minus 2 plus n. It's 2g minus 2 plus n because you're integrating over the fiber and you have the... if you remember, the universal curve was isomorphic to the moduli space with just one more mark point. And as you forget about that mark point, you collect the Euler characteristic of minus the Euler characteristic of the curve, and that's 2g minus 2 plus n. Anyways, you can just remember that kappa 0 is a number, of course, because the index is also the degree in cohomology. And so as the index is 0, that has to be a number. And the number is precisely 2g minus 2 plus n. And this 2g minus 2 plus n, you've seen it already at the end of the last session. If you remember, we introduced Svira-Solo constraints, and we saw that the first two were giving precisely the string equation and the dilaton equation. Okay, so those are the psi classes and the kappa classes. And then we also saw that you can take a locus of curves, if you remember. And this locus of curves, this loci of curves can be singular. If they are singular, they have a certain amount of nodes. And they can only have nodes as singularity. They cannot have cusps or any type of very singular points because when we took the Riemann-Mumford compactification, we restricted the singularity that we consider acceptable in our moduli space. We only took nodal curves and not more than nodal. We don't allow for singularities which are worse than nodal. So everything that is singular is nodal, and we are interested in counting how many nodes we have. Why? Because if you remember, every node is a shrunk dimension. Every node, you can consider it as the limiting curve of a family of non-singular curves there that degenerated to a node when I take the loop that is of length epsilon, and that gets shrunk to a point, okay? So every node is a shrunk dimension. It's a shrunk real dimension because I'm considering the length of the boundary and I'm sending that length to 0. So you may complain, you may ask, why, if I'm shrinking one real dimension by one complex dimension, that doesn't add up? I lost one dimension and I don't know where. I need to lose two real dimensions to account for one complex dimension. So where's the other real dimension? And then we mentioned this Weil-Peterson volumes and this Fenchel-Nielsen coordinates, where you can basically construct. This is very much related to Mirzakhani's work. Probably those of you who are interested in hyperbolic geometry know this very well, but somehow you can think of your surface as a collection of, you can subdivide it into pair of pans. This is something we have done together. And as you decompose it into pair of pans, you know that you only have one hyperbolic structure on each pair of pans because the length of the pans determine completely the hyperbolic structure on the pair of pans. This is not surprising because we learned that M03 bar is just a point. So you have no dimension. You don't have any moduli when you have an object that is genus 0 and 3 mark points or 3 boundaries, let's say after you fix the length of the boundaries. And so this is not surprising, but also when you take several pair of pens and you glue them, you have two parameters, two real parameters. You have the length of the boundary, it has to be the same on both sides, otherwise you cannot glue. But also, you can twist. So you can attach them, let's say, take a point of reference on each of the two loops of the same length. And when you glue them, you can glue them straight. You can let's say the origin of the first loop match the origin of the other loop, or you can apply a rotation of a certain angle. That angle is the second real dimension that is lost when you shrink that loop to zero. You're not just sending the length to zero, but you're also completely forgetting about that angle. So you're losing two real dimensions and you're trading that for losing one complex dimension. And so, sorry, today it's a lot of recall, but I think it's useful because, the first two lectures were just on Wednesday and Thursday of the same week. And also when you go through the first lectures, there's not much to remember because you just started. But today is the third lecture and a week has passed. And also we covered some material. So it's always good to be somehow on top of the material that we've covered so that we are all on the same page. And if somebody missed some lecture or some part of the lecture, is also an opportunity to go back on track. So basically, when you consider singular loci of curves, you want to count the nodes, and you want to remember that every node is the limiting procedure of a family of smooth curves that generated in that node, and therefore every node accounts for one less complex dimension compared to the open moduli space. So codimension 1, every node represents codimension 1. And also, if you remember, we saw how to associate to loci of curves stable graphs. So if you remember, to every connected component, we wanted to associate a vertex. And to every node, we wanted to associate an edge. And also to every mark point, we wanted to associate a half edge. And then we saw that the whole set of half edges was subdivided into this half edges of an edge and mark points that we called leaves. And then to every vertex, you want to associate an integer number, non-negative integer number that represents the genus of that connected component or vertex. And then when you consider a dual stable graph that is constructed like that, the number of nodes, the nodes correspond to the edges, so you can just count the number of edges, and then you know what is the codimension in homology. But as you take the Poincare dual of that, you're landing in cohomology, and now you need to reverse the dimension and the codimension, right? So now the codimension becomes the cohomological degree. And so now we just reproved together that the number of edges of a graph is precisely its cohomological degree in cohomology. So for example, if we look at this mouse dual graph, we can count the edges. Here we have 1, 2, this is a double edge, so 3 and 4. And also here we have a self loop, so self edge, 5. So we have 5 edges. And so this is something that lives in the age 5 in the complex sense. So in age 10 in the real sense, if you prefer. And we also want to remember what is the genus here, and the genus here. Let's say that here we have G1, G2, and G3. And let's look at the mark points, 1, 2, and 3. So now this guy, the Poincare dual of this dual stable graph, lives in the age 5 of MGN bar, where n is clearly equal to 3, 1, 2, 3. And now we want to determine G. Let me remind you how to determine G. The genus is now split into two different data. The genus, you can obtain it as the arithmetic genus, as the sum of the genera in the vertices, so G1 plus G2 plus G3. But then you need to sum up also the genus that is lost in, it's not lost, but is encoded in the graph. So you want to add to that the first Betti number of the graph. And so here we see that this graph has a self-loop, so has one genus hidden here, and one genus in this loop, and one genus in this loop. Okay, so just to make it clear, you have one here, one here, and one here. So you have 3. So the Betti number of this graph is equal to 3. And then you have the G1 in this connected component, G2 in this connected component, G3 in this connected component. So the total genus is G1 plus G2 plus G3 plus 3, and n is equal to 3. And this lives in age 5. I hope it's clear how to count things now. And then the other missing guy that we saw was this Hodge bundle, if you remember. So for every curve, you want to consider the vector bundle of its holomorphic differentials. Okay, so we know, I mean, this is, I think, very well known from standard course in Riemann surfaces or differential geometry, that this space is a vector space of dimension G. So you have G linearly independent holomorphic differentials on a curve of genus G, and therefore the bundle has rank G. If a bundle, the bundle on the moduli space, if a bundle has rank G, then you're allowed to take its Chern classes up to the Gth Chern class and not more, because I mean you can take the G plus first Chern class if you like, but that is for sure equal to 0. So there is no point in taking it. They will just vanish after the rank. And also lambda 0, which is the 0th Chern class, then it's just equal to 1. So that's also like, you know how to compute this. I mean, it's just 1. It's not so interesting. So the interesting ones are lambda 1, lambda 2, lambda 3, up to lambda G. Those are the interesting ones. And those are just the Chern classes of the Hodge bundle. And we also saw that, if you remember, when we were looking at nodal curves, there the holomorphic differentials are not holomorphic anymore, but because of this calculation in the local description of a node, that was described as x times y equal to t for some parameter t that was going to 0. Then if you compute the differential there, you realize that you can allow yourself simple poles, but with opposite residues on the 2 branches of the node. So these holomorphic differentials, they are not holomorphic anymore. They can have simple poles, but just simple poles. And also the residues must be opposite on the 2 sides of the nodes. And that was our definition of abelian differentials. So you have to extend from smooth curves to nodal curves. The holomorphic differentials become abelian differentials, and this rank G Hodge bundle also extends to the nodal curves. And so now you can take the Chern classes on the whole MGN bar with the Riemann for compactification. So that was our procedure. And so now, sorry for the long recall, but I think it was useful. I mean, if I was a student, I would have liked some recall. We basically recall the whole course in just 30 minutes, even less. So now, I mean, we can just look at this collection and hopefully we remember what we're talking about. We have psi classes, we have kappa classes, we have Poincare dual of stable graphs, and we have the lambda classes, which are just Chern classes of the Hodge bundle. And these are first Chern class of the cotangent bundle. These are first Chern classes. These are powers of first Chern classes, but pushed forward. And these are not first Chern classes. These are all of the Chern classes of the Hodge bundle. Okay, and I will refer to this as tautological class. Then you can combine them, of course. You can, I mean, once you have those protagonists, you can just start intersecting them and consider whichever combination of, you can do whatever you want. You can consider psi 3 to the power 17 times kappa 5 times kappa 3 times lambda 2 times the graph that you like, the mouse graph. You can do whatever you want. Okay. Okay, so let us now go through the definition of this tautological ring that I was referring to earlier. So the definition of tautological ring is run simultaneously on all of the GNs. So you're not allowed to define, I mean, if you want, you can, but that's not how usually people do it. People usually define the tautological subring of the cohomology of MGM bar simultaneously on all G and N, which are stable, of course. So you just discard Gn, as we said. Gn equal to 0, 0, 0, 1, 0, 2, and 1, 0 are the bad cases, if you remember. So the Riemann sphere with 0, 1, 2 mark points, and the torus without any mark point. So except for those 4 bad guys, you take all the other Gns, and now you define the tautological ring. Usually is referred to with is indicated with the letter R. So RH is the tautological ring in the cohomology, because you also have the tautological ring in the Chow ring. I mean, the tautological subring of the Chow ring. But now we care about the cohomology. You can define it RH up to star of MGM bar as a subring of the whole thing, whenever 2G minus 2 plus n is greater than 0, to be the smallest system of Q subalgebras. We are considering cohomology in Q. It's not super important, but somehow, like, since we have a complex orbifold, we always divide by the cardinality of the finite group that is acting on that chart, because it's an orbifold, and therefore you always have fractions, no? Because for example, you consider the moduli space of elliptic curves. Every elliptic curve has an involution, so you always have that generically the automorphism is group has cardinality 2, because you can send y to minus y in the equation y squared equal to x cubed minus ax plus b. So you have that involution, and so you have a group, you have z over 2z generically, and so you have, every point is a half point. You always weight points by the inverse of their cardinality of their group of symmetries. And you have 2 special elliptic curves. One has 4 symmetries and the other one has 6 symmetries. So you have 1/4 of a point and 1/6 of a point, but every other point has weight 1/2. So that's why people want to do, I mean, Q is enough because you always have fractions, and Q accounts for all fractions. That's the reason. So it's the smallest system of Q subalgebras containing the fundamental class, of course. I mean, how can the fundamental class not be tautological? That would be absurd. And also, I mean, this is the most important part, you want this system of Q subalgebras to be closed under pullbacks and push forwards of all the 3 tautological maps that we have seen. Of course, you would expect the tautological maps to play a role in the definition of tautological rings, and so it happens. If you remember, the tautological maps were pi, sigma, and rho. Let me remind you what they do. Well, pi, we just recalled, is the forgetful map. So you forget about the last mark point, and then you stabilize as needed. And sigma and rho are the 2 tautological maps that glue different connected components. So if you remember, there are 2 cases. Either you glue something that was disconnected into something that is now connected, or you glue 2 mark points of something that is connected, and then you create a node in the genus, like as if you were pinching a B cycle. So these 3 are the tautological maps. Each of them has well-defined both the pull back, which is the easiest, but also the push forwards are well-defined. And now you want to construct the smallest Q subalgebras containing the fundamental class, and which they are closed under pullbacks and push forwards. And that's the reason why we want to define tautological rings over the modular space of stable curves simultaneously on all G and N. And now it's clear the reason why we want to do it simultaneously, because these maps, they connect modular spaces with different G and different N, right? So if you now want to define a tautological, you can just one G and one N. It doesn't make sense to use these tautological maps for it. You would need to come up with a completely different definition, but not this one, because you want to be able to use these tautological maps over and over and over and over to just take fundamental classes of some graphs and push it forward and pull it back towards like different maps and go around. And now you're asking, like, what is the smallest possible thing such that I always land inside a tautological ring? Okay, so if you want, the tautological ring is generated by the tautological maps. This is another way of thinking about it. It's an informal way of saying it, but you know. And then it turns out that in genus 0 and in genus 1, the psi classes have a formula in terms of stable graphs. Aha! But that's really good, right? Because if you allow the fundamental class to lie inside the tautological ring, then also immediately all of the stable graphs also lie inside the tautological rings, because what? I mean, the stable graphs, you can just construct them with the tautological maps. You just take a graph. It has different vertices. Take each of them and consider it in a different moduli space per se. And now you can just glue them, right? And as you glue them with the gluing tautological maps, you're building the graph. And so now you're sure by definition that any stable graph lies inside the tautological ring. Aha! So now we gained the right of considering all of the dual graphs and the Poincare dual inside the tautological ring. Very good. But now there is a formula that says that in genus 0 and in genus 1, I have the psi classes are just the formal sum of certain graphs. I'm not telling you which ones, but I'm telling you that there is a formula in genus 0 and genus 1. Aha. So you have psi classes in genus 0 and in genus 1. But now you can take the pullback of psi classes in higher genera. And it turns out that when you pull back psi classes in higher genera, they are expressed again as psi classes minus some defect. And that defect is, again, a sum over stable graphs, which are already inside the tautological ring. So you don't care about them. So now that you have psi classes in genus 0 and genus 1 because they are expressed in terms of stable graphs, now you have for free psi classes in every genera. Aha, but you have psi classes in every genera. Now you can push them forward with respect to the forgetful map. But before doing that, you can take the power that you like. And that's the definition of kappa classes. So now all of a sudden you prove that you have kappa classes in the tautological ring, all of them, because it has to be closed. And you're just using tautological maps to do that. And now you want to prove that you have lambda classes inside the tautological ring. And that's the most complicated proof. And actually, I mean, there is a theorem to do that. It's not very easy to see that is tautological just like that. I mean, graphs, psi and kappa are easy to see. We just did it together. But for lambda, it's much harder. And for lambda, actually, we're using a theorem. This theorem is due to Mumford in 1983. And Mumford computes the Chern characters of the Hodge bundle. And then, of course, you can take the total Chern class as just exponential of the sum of the Chern characters. So if you, so Mumford proves that the Chern characters are just sum of psi, kappa, and divisors. But you know that psi, kappa, and divisors are tautological. Therefore, the Chern characters of the Hodge bundle are tautological. Aha. But if they are tautological, if I take exponential of their sum, it's also going to be tautological, where the exponential is cut by the dimension of the space, of course. It's not an infinite series, it's a finite series because I just truncated at the right dimension. So now the exponential of the sum of the Chern characters is just the definition of the Chern class. And now when I take the Chern classes, it's just the polynomial that is given by, I mean, the sum with some maybe formal variable, and is going to give me the total Chern class of that. So now this is the proof via Mumford theorem that also the lambda classes belong to this tautological ring. Okay, so basically all four our guys are tautological, as expected. And here, now you can combine, now that you have these guys and you know that they lie inside the tautological ring, now you can combine them as you please, and you are ensured that you are always going to land within the tautological ring. So for example, let me take this graph. This graph has three components, one of genus 2, one of genus 0, one of genus 1. And moreover, I have a further genus dictated by the loop of the graph. So this graph has Betti number 1. So you have total genus 2 plus 0 plus 1 plus 1. So that's 4. And you have 1, 2, 3, 4, 5 mark points. So that leaves in M 4, 5 bar. And now this graph has 3 edges. So lives in age 3 or 6 in the real sense, and 3 in the complex sense. But moreover, now I'm decorating, so I'm multiplying. So I'm intersecting in homology, and I'm taking the wedge in cohomology with some other classes. For example, in this vertex, I can multiply by kappa 1. And on this half edge, I can multiply by psi class to the power 2. This half edge, I can multiply by psi to the power 3. And this leaf or mark point I can multiply by psi2. What does it mean that I place psi classes on the leaves or on the half edges? But because this can be mysterious the first time you see it, no? We say that you can multiply it. But what does it mean that instead of multiplying, I just place it in the right half edge? It means that I'm taking the first Chern class of exactly this mark point, right? So psi2 is easy to define, but now what does it mean that I take this psi prime to the power 3? I mean that so we have seen that every time that you have a graph, you can consider this graph as the gluing of all of its connected component, right? By the tautological maps. So when you degluing, when you separate, you can consider these guys separately. So this leaves in a smaller moduli space of genus 2 with 3 mark points, 1, 2, and 3. Okay, so in that moduli space, this half edge of an edge is now a mark point. So now you have the right to consider the cotangent bundle on it. And you have the right to take the first Chern class. And you have the right to call that psi class. So now when you glue it with something else, you can still remember that you used to have a psi class there. And that's the class that you're intersecting. So you always have to think that this graph is just a product of its components. And on each component, the psi class makes sense. And this kappa, why are kappa usually drawn within the vertex? Well, because there used to be an extra guy here, some leaf, maybe labeled 6, because we have all leaves from 1 to 5. So let's say that here there used to be some leaf labeled 6, and then we forgot about it. And so which psi class did we need to have there when we used to have this leaf number 6 in order to have kappa 1? Well, kappa 1 is the push forward of psi to the power 2, because remember that the push forward connects two spaces. It goes from mgn plus 1 to mgn. So I'm losing one mark point, and together with it, I'm losing one dimension. So I decrease the cohomology class by 1. Whereas if you take pullback, you don't augment it, you keep it stable. So the pullback preserves the degree of the class, whereas the push forward decreases it by 1 complex degree. So this used to be psi2 on this guy that was labeled 6. So this kappa 1 used to be psi 6 to the power 2, and then we forgot about the mark point, so it became kappa 1. And the reason why I put it inside this vertex is that this label, this mark point label 6 used to be attached to this vertex and not to this vertex or this vertex. That's why I'm putting it here. And I don't care if it was here or here or here, it was attached to this component, and therefore I just need to remember for kappa classes on which components they used to be attached as mark points, those psi classes that got pushed forward. Okay, so this explains basically everything that is written here. Oh, here I even drew it. We used to have this 6 with the psi 6 to the power 2, and then we forgot about the 6 and we took the push forward, so this became kappa 1. I even forgot, I didn't just forget the mark point, I even forgot that I drew it. Okay, and as we said before, there is a lot of relations between these generators. So as a generator for the tautological ring, you can consider not just stable graphs, but decorated stable graphs. That's my main point. You consider all possible stable graphs with all possible decorations. Decoration meaning that on each half edge, you can take psi classes to the power that you like. And on each vertex, you can consider kappa classes to the power, to the index that you like. And you can even take products. You can take, for example, kappa 1 times kappa 2 times kappa 1 times kappa 0, whatever you like. So you consider all possibilities, and those are the generators of your tautological ring. Of course, if you want to consider the tautological ring in complex degree D, then you just have to take the generators of total degree D. So, and the degree, as we said, is the sum of the degree of all the classes you decorated the graph with, together with the sum of the amount of, well, together with the sum of the amount of edges, because every edge corresponds to cohomological degree 1 complex. And then we spoke about these Faber-Zagier relations on MGN open. And then this list was then hugely extended by Pixton relations on MGN bar, which is still an open conjecture up to today. However, we have available the proof that all of the relations conjectured by Pixton are true. They do hold. The problem is, what if there is a relation that is also true, but is not in Pixton's list? That's the question that is open. However, I mean, people generally believe that the list is complete. But we don't know how to prove it yet. Okay, let me make an example. This is the famous Getzler relation, and it's nice because it's very explicit and you can draw it. This is in H4 real, so it's 2, it's H2 in complex sense of M1 4 bar. Okay, so genus 1 and 4 Mach points. So okay, let's have a look, because it's really if you've never seen these relations, it's not so easy to imagine how complicated they can be. So let's have a look at Getzler relation. It's a very easy one, but it's already quite complicated. So for example, you would sum over all of the subset I and J, so that the cardinality of I and J is equal to 2. So you take your subset that contains the points P1, P2, P3, and P4, and now you split it in two subsets of cardinality 2. So you can put, for example, the leaf 1 and 3 in I, and therefore you would put the leaf 2 and 4 in J, right? But in all possible ways, you have like 6 ways of doing it, right? And then here you have a vertex of genus 0, a vertex of genus 0. And where is the genus 1 gone? Well, it's in this self loop. So this would be the cross sum. This would be a self node, okay? So this is clearly genus 1 because it's 0 plus 1 is 1. And you have 4 legs, okay? Distributed in all possible ways. So you sum over all possible ways. And when you have this graph, then you take the Poincare dual. Of course, you have one edge and another edge here. So of course, the cohomologic degree is 1 plus 1, 2 complex, therefore 4 real. Okay, then you add the sum again of all possible I and J, but this time I has cardinality 1 and J has the other ones. So of course, now here you had 6 possibilities and here you had 4 possibilities. You still have this self loop, but now you have this coefficient 3. Why? Well, because it works. I mean, this is the relation. You have some coefficients that are not necessarily equal to 1. And then here you have this other guy, and now you realize you don't have to sum over I and J any longer because you have all of 4 mark points here. And now you could complain and say that, well, this component is now unstable because you don't have mark points. But in fact, it's not true, because if you look at it, I mean, you have one half edge connecting this component to this component, so you have one special point here, and now you have this self loop. The self loop has 2 special points, so this is a rational component with 3 special points, so it's M03 bar, which is a point and it's stable. And now you multiply this by the coefficient 6. Now this sum is equal to 3 times this guy. Well, you always sum over I and J, so you have 4 summons here. And again, this is genus 1 because you see that the graph has Betti number 1. And both of these guys are stable, of course. And then you take the Poincare dual, so it's in cohomology, and it's always in the right degree because you have 2 edges, and 2 edges gives you cohomology degree 4 real, plus 4 times the sum over I and J. Again, like here you have 6 summons because you have binomial 4 over 2, which is 6. And here again, you have genus 1, and here again, you have the proper degree, and everything is stable. So it all makes sense. Like what I wanted to say is that these 5 summons, they make sense. They are all inside this guy, right? And now Getzler is telling us that there is a precise linear combination of these guys that gives you 0. So they are not linearly independent. Then you have a relation, but it's quite a complicated relation. And how do you actually prove this relation? It's very interesting how you prove it, because I think you use this relation over here, and then you pull it back, but in a smart way. So this is a more fundamental and simpler relation, but now pulling back this relation produces for you more complicated relations. And this is called WDVV relation. Probably many of you have heard the WDVV equation or WDVV relation before, and basically states that if you consider the stable graph with 2 genus 0 components related by a node, and you put the mark points 1 and 2 and 3 and 4 here, that's the same thing as taking 1 and 3 and 2 and 4. So you can just swap, right? This for that. And they are the same in cohomology. But why are they the same in cohomology? The proof is beautiful. Because if you consider M04 bar, if you remember, there is a lemma in complex geometry that is saying that if you have the Riemann sphere, and you take 3 points and you tell me where I should put them, well, there exists and is unique a biolomorphism that does that. Okay, it's the same thing as the structure theorem for linear mapping. In linear mapping, I mean, we all remember some linear algebra, right? We have two vector space. Yeah, we have two vector spaces. And now let me consider a linear mapping between the domain and the codomain. Now let's pick a basis for the domain. Let's say it's finite dimensional. Everything is finite dimensional. There are no complications. Let me take a basis. Let me take this basis vector v1, vn, okay, dimension n in the domain. Okay, now if you tell me where I should put them, so if you give me the images of these vectors in the codomain, then I can assure you that there exists and is unique a linear mapping that does that. If you tell me exactly where f of v1, f of v2, f of vn should be in the codomain, then I can just extend the definition of that linear mapping by linearity. I define it on the basis vector, and then everything else is determined. And that's the same thing that was happening, the same principle that was occurring also on M03, in the sense that if you have the Riemann sphere, you take 3 points, you think of them as sort of basis vector in some sense. That doesn't make sense what I'm saying, but it's the same principle. Now you tell me where I should put them, and there exists a unique biolomorphism that is doing that. And so since I can choose where I put them, I always want to put them in 3 special points, which are 0, the point 0 on the Riemann sphere, the point 1 on the Riemann sphere, and the point infinity on the Riemann sphere. So I can always put them there. But now you tell me that I don't have just 3 mark points, I have 4. I have 1 more. And then I tell you that, okay, the first 3, I will put them in 0, 1, and infinity. And the 4th one, I cannot choose where I put it. It will be determined by this biolomorphism that brings the first 3 to this position 0, 1, and infinity. Therefore, the equivalence classes up to biolomorphism of these curves will be determined by the position of the 4th point. And the 4th point is free to go around the Riemann sphere, and every single position except the ones which are already taken, which are 0, 1, and infinity. Therefore, the moduli space M04 without the bar is just the Riemann sphere itself minus 3 points. And then we saw that compactifying that was giving us exactly the Riemann sphere, and we had to add 3 points representing 0, 1, and infinity. And if you remember, we knew exactly which points we needed and how we needed to represent them as stable graphs in lecture 2. So last time we saw that. And so now if you think about it, on the Riemann sphere, every point is cohomologous. Every point is cohomologous on the Riemann sphere. We know that from some bachelor course, or I don't know, maybe the master, but you can just move around the point and it will give you the same cohomology class. But now if you think of as the Riemann sphere as M04 bar, now one of these points, say the one at infinity, is representing this graph, and the one at 1 is representing this graph. But because they are cohomologous on the Riemann sphere, which is the moduli space M04, now you can say that in cohomology, what is represented by those points is also the same in cohomology. So the fact that the points are cohomologous implies that the stable graphs that these points are representing in the moduli space are also the same in cohomology. And that gives you this relation, which is the well-known WDVV equation. And now if you pull back this equation in a smart way and maybe do something else that I don't remember, you get Getzler relation. So this is a very beautiful story. These relations are quite non-trivial. I mean, you have way more complicated relations than Getzler relation, but this is I would say, the first complicated enough that we can write explicitly a relation. So maybe it's a good time to make a break. Okay. Yes, very good. So another example is given in the tautological ring of genus 1. So this is a theorem by Petersen. And the theorem is that all relations in genus 1 are given by Getzler relation and by the pullback of WDVP. So I mean, there was a time, especially like a few years ago, where people were really like starting from low genera, genus 0, genus 1, genus 2, genus 3, and there was this hunt for determining all of these tautological relations in small genus, and also maybe not all of them, but how to generate them. So for example, I mean, in genus 0, it's simpler, but in genus 1, this result is saying that basically WDVV and Getzler relation, the relations that we've just seen, are enough. But in genus 2, they are not. So of course you need to add something else. And somehow the ultimate answer to this should be Pixton conjecture. In general, relations can be quite non-trivial. And for example, if you consider genus 2 and n equal to 2, so in M22 bar, you consider the cohomology in complex degree 3, it has 161 generators, which are decorated graphs. And 14 of them are linearly independent after application of Pixton relations. So this for me is a good example. I mean, you can check with the CoCalc package as I suggested last time. You just go on CoCalc and you call the package ADM cycle. And you can also have a look at the paper, which is a great paper on the archive, this ADM cycle paper by Delacroix, Van Zelm, and Johannes Schmidt. I use it a lot, and also we organize several events, several conferences and workshops and PhD schools where we use this software and we implemented new functions and so on. And we asked, actually it was very nice, we asked to the researchers in the field what they needed, which kind of functions they needed. And then we were in the mountains for a week altogether, just coding those functions. And then we made some report about it. So it was a very nice experience. And I think several students were also had fun and learned hands-on how to do these things. In any case, you can just use it now. So just it's available for free. You just call ADM cycles, and if you don't know how, you just look at the paper or at the previous slides of the session 2. But anyways, here you have 161 generators, which are a lot. I mean, to for example, list by hand, it would take a while, right? And but only 14 of them are linearly independent. So you see that the amount of relations is huge compared to the amount of generators. Let me make another example. I consider this guy, this graph, this decorated graph. And now we have seen dual graphs arise from products of smaller moduli spaces. And now if you look at this guy, you can focus on each individual connected component. And therefore you have like here a genus 2 connected component with 3 special points, and you just have psi class here, let's say to the power 6. I mean, if you take power 3, it's okay, but you don't get a number. But if you take power 6, because the dimension of this guy will be 3 times the genus, which is 3 times 2, which is 6, minus 3, so that's 6 minus 3 is 3, plus the amount of special points, which is 1, 2, and 3. So that's 6. So if you want a number, you need to augment this psi class to 6. And now you have the integral of psi 2 to the power 6. And we saw that, I mean, you can use several tricks to compute this number. One of these is a string equation or Dilaton equation, or the Dijkgraaf equation that would tell you that the integral over mg1 of psi 1 to the top power, so 3g minus 2 is the number that you need for this to be a number. So the exponent that you need for this to be a rational number. And the answer is 1 over g factorial times 24 to the power g. So this is a well-known result from Dijkgraaf. And now if you have at your disposal string and Dilaton and Dijkgraaf equation, and sometimes you would, if you do computations in higher Geneva, you would also need the other Virasoro constraints that we've seen. But in this case, this is low enough for these instruments to be enough. So now this number here would be just 1 divided by 1152. So just 1,152. That's the result of this integration. And this integration is equal to 1, if you remember, because you're integrating over M04. So this is just P1. This is the Riemann sphere. And now you're integrating a psi class to the power 1. But you also have psi 1 to the power 0, right? Because you don't have any psi 1 or any psi 3 or any psi 4. So you can pick each of these 3 missing psi classes and you apply string equation there as we see last time. And then you end up with the integral over M03 bar, which is just a point. And you're integrating 1 over a point. And the integration of 1 over a point is just 1, right? You don't have like any orbifold sort of automorphism there. So yeah, the answer is just 1. So this would be the integral attached to this guy here. You have like just some genus 0 with 4 mark points, and on the second one, on this leaf mark with 2, you have psi 2. So then you just do that. But when you do that, you apply string once, and then you end up integrating over M03 bar of just psi to the power 0, and that's equal to 1. And then the missing one, the last one would be this component here, which is of genus 1 with 1, 2, 3, and 4 mark points, and you have a kappa 1. So here you're integrating you're integrating psi 1 to the power 2 times psi 2 to the power 1 times kappa 1, and you want to calculate this over M1 4 bar. So the first thing that you do is to compute the dimension of this guy. The dimension of this guy is 3 minus 3 plus 4, so it's equal to 4. The dimension of this is 2 plus 1 plus 1, which is also 4. So they match and you have a chance to get a number out of that. And now basically you want to apply what is called projection formula. So how does the projection formula work? Remember that this kappa 1 is just the push forward of psi to the power 2. Which psi? A psi that was forgotten. So if here we have like 4 mark points, you can think that this used to be psi 5 because 5 is missing. Psi 5 to the power 2. And so now, because this is the push forward, when you apply the projection formula, you can just take this class without the push forward. So you have like psi 5 to the power 2. But now you take the pullback of these guys and you integrate over M15 bar. And now you can compute you know that the pullback is always a ring isomorphism, whereas the push forward is not. So when you have the pullback is much better. Pullback of the product is the product of the pullbacks, but that's false with the push forward. So now you can just split into pullbacks of these guys, and you can complete, if you know what the pullback of one psi class equal to, then you can just compute it all. And in fact, the pullback of one psi class is just the same psi class minus a stable graph that you can control. And so out of this relation, you can just compute a number, and this number is 2/3. And now if you compute the product of these numbers, you get this beautiful 1 over 1728, which comes from the J invariant of the elliptic curve. So this is an example of how you take these stable graphs in which the dimension matches the homological degree perfectly. You split it into the integration over each vertex. You compute each of them with all these tricks, like either projection formula, or string equation, or dilaton equation, or Dijkgraaf equation, and those are enough to compute everything. So in general, how do you intersect things, like different things? For example, what if you have psi 5 to the power 7 and you want to intersect with psi 6 to the power 3 and kappa 1? Well, this is just this monomial that we just intersected before. I mean, a similar one. But what if you want to intersect this dual graph with psi 3? Well, then you basically place psi 3 on the edge, on the half edge marked with the letter 3. Okay. And then you just compute as before. You computed the integral of this vertex times the integral over this vertex. So as an example, you can see that if you take this dual graph and you intersect with psi 3 to the power 2, it's the same thing as placing psi 3 to the power 2 on this guy. And now you can just integrate over M0, 1, 2, 3, 4. So over M04, you integrate psi 3 to the power 2. And this is 0. Why is it 0? Well, because this moduli space has dimension 1, 2, 3, 4, minus 3, so dimension 1. And here you have a cohomological class of degree 2. complex degree 2 against complex dimension 1. So of course it's too much. This class is too much for this space. So there's not enough space to integrate this class. So the result is 0. Whereas if you were to integrate psi 2 to the power 2, that is not 0. Why? Because now you're not placing it here any longer. You're placing it here. But the dimension of this space is very small because you have genus 0. So genus 0, the formula is 3 times genus minus 3 plus valency of the vertex. But now, so here it would be like 4 minus 3 is 1. But here you have genus 1, so it's much larger. You have a summand of 3 to add. Now the dimension of this guy is 3 minus 3, which is 0, plus 3, because 1, 2, and the half edge is 3. And now if you're integrating a class of degree 2, that doesn't automatically vanish for dimension reason. Actually, in order for it to be a number, I mean, that would be just a class that is not 0. So it is correct that it's not 0, but it's not a number that is not 0. It's a class that is not 0. So if you would intersect this guy with another psi 2 or another psi 1 or another psi on this half edge, then you will get a non-zero number. So far, it's just a non-zero class. Okay, so intersecting dual graphs and psi and kappa is sort of easy because you just place them where they should be, use projection formula, and so on. And then you just do your computation. I'm not saying that is something that is very quick to do. Sometimes it takes time. Sometimes it takes a lot of time. But it's like, I don't know, reducing a matrix in its echelon form, or like inverting a matrix. It's not particularly complicated. It's just maybe very long, but you know exactly what to do. You just have to do a lot of calculations, right? So it becomes a little bit like linear algebra. You just patiently use all the tools at your disposal one by one. Usually you have a huge amount of graphs, and it's very easy to forget one. And that's why we use computers to do that. But in principle, like the procedure per se, it's not complicated. Okay. But so far we integrated psi with graphs and kappa with graphs and psi with kappa with graphs, but we never intersected graphs with graphs. How to intersect graphs with graphs? So let us have a look at this example. I want to intersect this dual graph with this dual graph. And so this dual graph is telling me that the leaves marked 1 and 2 are separated from the leaves 3, 4, 5. Whereas this graph is telling me that 1, 2, 3 are separated from 4, 5. So how do I accommodate both of these linear conditions at once? Well, I just add a bubble here, and I put the number 3 here. So now, indeed, there is an edge that is separating 1, 2, 3 with 4 and 5. It's this edge over here, right? But now there is also an edge that is separating 3, 4, 5 from 1, 2. That's this edge over here. It's a different one, but there is one, right? And also, you can complain about the codimension, right? Say, but is the codimension right? Are you sure? Yes, I'm sure, because here you have just one edge. So this is going to be cohomological degree 1 complex. This is also 1 complex. 1 plus 1 is 2. And indeed here I have 2 edges of the graph. So that's correct. It matches. So this is a very easy example because you have, one edge here, one edge here. But in general, intersecting graphs can be very complicated because instead of resulting in a single graph, you may have a huge sum of graphs. So you would need to take the formal sum over all stable subgraphs of both. That's the proper way of doing it. And that's also why we use computers, because the number of graphs grows extremely fast. Actually, the number of stable graphs of genus G with n mark points grows like 6G minus 6 plus 2n double factorial. So it's really a factorial graph. It's much more than exponential. It's not something that you want to do by hand, other than for like a very, very small genus and very, very small number of mark points. Okay. What about self-intersections? How can we intersect a stable graph with itself? How does it work? Because you just told me that now I'm from the point of view of the students. You just told me that I need to take the sum over all possible subgraphs, but if I now intersect the graph with the same graph, then subgraphs are just the graph itself, so it doesn't make much sense, right? So that would be a fair question, and the answer would be the following. Let me take, for example, this graph over here with 3 mark points on this component and 2 mark points on this component, and this is an edge, or equivalently a node. No? We know that nodes and edge are the same thing. It's in the dual picture. And let's intersect this with itself. So how does it work? In intersection theory, usually when you take self-intersection of something, you want to deform it a little bit. So you take one of the two copies, you deform it slightly, and then you intersect, and then you take sort of the limit when it goes back to itself. So you want to wobble those things and make them a little bit more generic and get the intersection this way. So we wiggle this component in a bit of a generic position, and then we intersect. So what do we get? Since we have one node, we need something of cohomological degree 1. What do we want? We want, generically, what we need is the first term class of the bundle that is normal to this node. So because we're intersecting with itself, we want something that is normal to the node. And because it's codimension 1, we want the first term class. So we want to compute, that's the rule. I'm not saying why, but I'm saying how it works. The rule is to take the first term class of the normal bundle tangent to the node. So then what does it mean? That you would get the tangent space on one branch of the node plus the tangent space on the other. Okay, so you get this third sum of tangent spaces. But now the first term class is additive towards with respect to the direct sum. So you can now split this into the first term class of the tangent space on one side of the node, on one branch of the node, plus the first term class on the tangent space on the other branch of the node. But now instead of tangent spaces, I want to take cotangent spaces, or cotangent bundles, sorry. Why? Well, because I know what is the first term class of the cotangent, right? It's just the psi class. So now let me change from first term class of the tangent to the first term class of the cotangent. And the only thing that I need to modify here is just take the minus sign, because I'm taking the first term class of the dual is just minus the first term class of the non-dual. And so now here I will get this cotangent that we used before on one branch and on the other, but now I have the minus signs. So now this, I recognize it to be psi class on that branch of the node, and this, I recognize it to be psi class on the other side of the node. So basically, now I want to compute, I want to conclude that the self-intersection of this dual graph is just equal to this graph times this first term class. Therefore, is this graph times minus psi prime plus psi prime prime in parentheses. And when you apply the rule here, what do you get? You get the graph, but now you take minus the psi class on one branch of the node plus minus the psi class on the other branch of the node. And that's how you self-intersect graphs. And dimension-wise, it all makes sense, right? Because you had codimension 1 plus codimension 1, that's codimension 2. And here you have codimension 1 for the edge and codimension 1 for the psi. So it matches. Okay, very good. So we also know how to self-intersect graphs. And now we can have a look at our intersection theory toolbox. So here I'm listing several equations that we mentioned or we used before. The projection formula, we definitely mentioned it, and it's very, very useful one. And it works like that. If you take the push forward with respect to the forgetful map of some class times the pullback of another class, beta, that's the same thing as taking the push forward of alpha times beta without the pullback or the push forward. So somehow, okay, naively speaking, you can think that these two guys are simplifying, but only for beta. So it's not true. So let me remind you that the pullback is a ring isomorphism. which means that pi upper star of the product is the product of pi upper stars. But with the push forward, that's not true. So it's not true that you can say that this pi lower star of alpha times this guy is just pi lower star of alpha times pi lower star of pi upper star of beta. That's not true. But somehow in the projection formula suggests that, I mean, just as a way to a mnemonic rule, you can think that it just picks up the first one and it simplifies against the second one, naively speaking. That's not mathematically correct. It's just a way to remember it. And now, how do you use projection formula in practice? It's very useful. It's extremely useful. You can just say that the integral over mgn plus 1 bar of some class times the pullback of some other class, that's just equal to the push forward of the first guy times the second y without the push forward. So this is extremely powerful. And now, of course, where do you need this equation? Well, for instance, with all kappa classes, because all kappa classes are defined as push forward of some psi. And you really like the psis because they're nice guys. They're fundamental objects of the cohomology, right? So you want those guys, but they are trapped inside this forgetful morphism, and you want to get rid of this. And how do you get rid of this? With projection formula. So projection formula is extremely useful, and in particular is particularly useful with intersection of kappa classes. Then the other thing that you want to use is that how do you compute? I mean, we mentioned this, but we never actually looked at the formula. How do you compute the pullback of psi1, of psi I? So psi I on mgn, and then you take the pullback, is equal to psi I to mgn plus 1. So this lives on a different moduli space than this, right? Because this has one, I mean, there is a difference of 1 mark point, right? This is on mgn plus 1 bar, whereas this is on mgn bar. But then it's not true that the pullback of psi is equal to psi. There is a defect, as I mentioned, and this defect is exactly that thing. Is you just have a component of all the genus is concentrated here, and you have all mark points here, except that here you're bubbling a rational component, genus 0, and attached you have 2 mark points. The last one, this is the one that you're going to forget about, and this is the mark point I. Okay. And indeed, like one thing that you immediately see is that just consider this graph and forget about the n plus first mark point, right? You just forget about this mark point. Then you end up with a rational component with 2 special points, this half edge and this leaf labeled I, right? But you know this is unstable because the Euler characteristic is not negative. It used to be stable with this guy, but as you forget about it, it's unstable. And we saw that the normalization procedure, the stabilization procedure for this guy is just to contract this rational component entirely and just to attach this mark point I directly to this genus G guy. Okay. So you see that, I mean, it makes a lot of sense to consider this particular graph because as you are forgetting the n plus first mark point, you're going to get back exactly the fundamental class of the moduli space. So it makes sense that this guy is here in the defect of this formula, but of course you need to prove that you have nothing else, right? And then I gave an exercise, which is, okay, now if you know the formula for one psi class, can you compute the formula for the nth power of a psi class? I mean, and the trick is just to, you use the fact that this pullback is now a ring isomorphism. So now you can exchange the power m with, you can say that this guy is now the pullback of one psi class, but to the power m, everything to the power m, because it's a ring isomorphism. And now you can just use this formula to the power m. And now you have to intersect in all possible ways. You get sort of binomial theorem. But now you have to, when you intersect, many of these things will give you 0. And as you get a lot of zeros, the result is this guy. So this is a very good, I mean, it's a very simple exercise, but it's a very good computation to do if you've never done it before. Okay, then similar things you have with kappa classes. So here you have the pullback of kappa is also kappa. Again, these two kappas live on different moduli spaces, of course. Okay. But that's not all. Like pullback of kappa is kappa, but then you also have a defect. And the defect is psi n plus 1 to the power m. This also makes sense that you have this defect here, because look, this m is the same as this m, so they are in the same degree, which you expect because it has to be homogeneous. But on the other hand, like as you push forward this guy, you're going to get a kappa class, but kappa m minus 1. So it kind of, I mean, it's very resemblant of the definition of kappa class itself, and there is a reason for that. What else do I want to put in our intersection theory toolbox? Well, the fact that, for example, if you take alpha, you take the pullback and the push forward, you're not going to get alpha. And also, if you take the first the push forward and the pullback, you're also not going to get alpha, nor the other guy. You're going to get 3 different things. They are not even the same dimension. The upper, so the pullback is ring isomorphisms and the push forward is not. That's something that we said several times before. And then we have the sphere circumstance. Well, those ones we had to look at in the second session, so last time. And we saw that we have a collection of these differential equations for m that goes from -1 up to infinity. And for the first value, m equal to -1, you have the string equation. And for m equal to 0, you have the dilaton equation. And for m equal to 1, you have something else that you can compute, and it was an exercise left to the reader. And then also you have some initial data, like, okay, you need to know that the integral over m03 of nothing is equal to 1. The integral over m11 of psi over 1 is 1 over 24. And also in general, like the integral over mg1 of psi to the power 3g minus 2 is this guy. This is also a formula that we've seen before. So the collection of all of the Virasoro constraints and all of this initial data and all of these tools allow you to compute basically every single integral of every single decorated graph you can think of. So just take any graph you want with the genus distributed however you want, you decorate it with psi and kappa as you please, then these informations are enough to compute the number as the result as a number. Okay. I mean, you also want number 7, but I mean, this is something we've seen already. This kappa 0 is equal to 2g minus 2 plus n. And those are the formula for psi classes in genus 1 and in genus 2, in genus, 0 and in genus 1 that I promised before when we were defining these tautological rings, if you remember. Psi I, you can express it like that. It looks a little bit funny, but there is a very nice proof that I would recommend reading on the Dimitrov-Zvonkin notes. And basically, it's very nice because you want to express psi I, but now the rule tells you that you're free to pick any j and k that you like. Any two. It doesn't matter which ones you pick. Just pick 2. It would work for any 2 you pick. Just put them on a component that is not the component on which you attached I. And put one single edge there. And now you just distribute all of the other mark points the way you please. But of course, here you will need to have a cardinality of I, which is at least 1, because otherwise this will be unstable. Provided you put at least 1 mark point here, this is stable. And for the rest, you can do whatever you like. And you can pick any j and k, it will work. And the proof of this is because this is the first chain class of the cotangent. So we've seen that you can pick any meromorphic section you like and just compute zeros minus poles. And basically, you can always construct a holomorphic differential, well, which would be meromorphic because you have nodes, but you have a 0 on one of the things. No, yeah, you take a residue 1 and a residue -1, I think. And then you have a chain of rational curves in a tree that propagate this condition that the residue is opposite to one another. And now you look at the locus where this meromorphic section is equal to 0. And that's 0 precisely when j and k are on the same component, but they are not in the same component as I. And now, since you want the first term class, you just take one edge. I think this is more or less the proof, but I mean, it's better to read it on the Swankin notes. And I didn't provide here the full proof because it was too long, but it's very nice, and I think it's very concrete. So I think it clarifies a little bit more and more concretely what we are doing. So I would, if I were you and I wanted to understand, I would go and look for this particular proof. So in any case, in genus 0, you have this formula. So again, psi class as a sum of dual graphs. Again, this is in cohomologically complex cohomological degree 1. And this is as well because you have one edge, so it makes sense. And now in genus 1, you have the psi I is equal to the rational component with all mark points and one half edge multiplied by 1/12, plus the sum over all I and j distributing mark points. And the point labeled I, you have it on the rational component, and you have genus 1 here. So, I mean, you see, it's very nice formula that allow you to explain, to express psi classes in terms of graphs. And then you can compute more psi class, kappa classes. For example, let's take the integral over m05 bar of kappa 1 to the power 2. Again, let us first check that this makes sense. This space has dimension 3 times the genus minus 3 plus 5. So the result is 2. This has dimension 2. And kappa 1 has dimension 1, but I have it to the power 2, so this has degree 2. Degree 2 and dimension 2, so I will get a number out of this. Okay. So what can I do? Well, I take a kappa 1 and I express it as the pullback of psi 6. Right? To the power 2, of course. Then I use projection formula, so I do get this psi 6 to the power 2. But I also have to get the pullback of the other kappa 1. But kappa 1, what is the pullback of kappa 1? It's kappa 1 minus psi 6 to the power 1, if you remember. This was the formula for the pullback of kappa 1. So now you can write this as the minus the integral over m06 bar of psi 6 to the power 3 plus psi 6 squared times kappa 1. So now this guy is equal to 1. I mean, you can use the string equation 3 times and get 1 as a result. It's very easy. So you get minus 1. But this guy, you need to use projection formula once more. You use projection formula once more, you get psi 7 to the power 2 times for this kappa 1. And now you need to get the pullback of psi 6 to the power 2. So what is the pullback of psi 6 to the power 2? If you did the exercise that we mentioned before, you know that you will get psi 6 to the power 2 again. So it's the same guy, minus some correction. In this case, it's plus because it's minus 1 to the power m, if you remember, m is 2. So it's a plus. This graph that has the right dimension. And so now you just intersect, you get minus 1 plus the integral over m07 bar of psi 6 to the power 2 times psi 7 to the power 2 plus 0 for dimension reasons. And so now you just have to compute this guy. You use string equation. I went too far. You use string equation. And you're getting, again, so string equation, if you remember, you decrease the power of psi classes by 1 in all possible ways. So you can either decrease it here, the power of psi 7, or you can decrease here the power of psi 6. So you see that you used to have 2, 2. Now you have 2, 1 plus 1, 2. Okay, minus 1, which was the first summon. And now you use string equation again, or Dilaton equation. Here is better to use Dilaton equation because you have psi to the power 1. So if you remember when you use Dilaton equation, you need the psi something to the power 1. Now you're getting rid of that. You're decreasing the number of mark points by 1. That's the rule. And you're multiplying by 2g minus 2 plus n, where g and n are of the space of arrival. So here's 3. And here again is 3. So now you're computing just 3 times the integral over m05 bar of psi 6 to the power 2. And that's equal to 1. And this is also equal to 1 for the same reason. I mean, it's basically the same integral. I mean, you get from here to here with the string using the string equation once. It's just a matter of using string dilaton and the same tools over and over. So you're getting 3 plus 3 minus 1, which is 6 minus 1, which is 5. So at the end of the day, you can conclude that the integral of kappa 1 to the power 2 is equal to 5. But you see, like, this integral looks very simple because you have just kappa 1 times kappa 1. And the result is also very simple. It's just 5. But along the way, you had to explode this expression into a more complicated expression and use a lot of times projection formula and string equation and dilaton equation before you could reach the result. So and this is the case for many computational modular space of curves. It gets harder before it gets easier. So it looks easy and the result is also easy, but along the way, the formula becomes much more complicated before you can start simplifying it. Okay, so I feel this is enough for today. I don't want to overload the session with information. So we'd rather just stop now and continue tomorrow.